Welcome, static students. This is the first lecture in our series on structures, which include trusses, frames, and cables. Sometimes you'll hear frames and machines put into the same category. And in this section, we're going to take all of the equations and equilibrium analysis that we have used up to date, some of the forces being zero, some of the moments being zero, an understanding of support reactions and the number of supporting forces or moments that can be applied, and how to do free body diagrams and apply Newton's third law for action and reaction of one body against another, transferring of contact forces. And we're going to apply it to types of structures for which we can have specific shortcuts. And that is especially true of trusses. So no new concepts, but repackaging of the concepts that you should already have at this point, such that you can really simplify your analysis for these particular structures and take advantage of those simplifications to create and analyze things that are more complex. So we'll just start in here. In every case, we will have options for analyzing the structure by cutting through it, through intact components, and evaluating the forces and moments at the cut. Now this is I guess I should step back. This is a new concept, and it's although we're not introducing a new analysis of equilibrium, the idea of cutting through something and then applying the conditions of equilibrium at a cut surface is a very new application. Up till now, depending on the course of your study, you have looked at only external forces and moments. So you had either a particle that really didn't have any size, and so it had no internal aspect because it had no size, or you looked at a rigid body only on the outside. So it could translate or it could rotate if the sum of the forces and moments wasn't zero. But it really didn't matter how those forces were applied. You could create an equivalent resultant force moment system that would produce the exact same translation and rotation. Well, what we didn't look at was what was going on the inside of the body. And although that is generally not the province of statics, that's something you'll look at in mechanics of materials and other types of courses more towards material science, we can do very limited exercises looking inside a rigid body, still going to be rigid, no strain allowed, by doing cuts. And when we get over into beams, we're basically going to do a moving cut and look at what's going on under very specific loading conditions. So when we start into trusses, we're going to look at what happens when we take an intact rigid body and we cut it. And we're going to look at what is the effect of the forces coming from the rest of the body on the other side of the cut to keep each of the two cut pieces in equilibrium, because they're still not accelerating. So that's something we'll get to and introduce right in this lecture. So that is the only new concept, but it's not really new because it will still be application of conditions of equilibrium, just in to two pieces that used to be one, across a cut. Okay, on to trusses. What are trusses? They have a very specific definition, and that's what that specific definition gives us all of our simplifications that we can apply. So first of all, they're idealized structures. Real structures can approach the ideal to acceptable approximation, which is why you're studying it. Otherwise, we wouldn't be studying it. What are those characteristics? First, you've got straight, slender bars. So slender means the bar is very long in comparison to its cross section. So you can have something with, a 2-foot diameter cross section. It better be like maybe several hundred meters long. That would fit. Connected by frictionless pins or a 3D equivalent, which would be a ball and socket. So no moment applied at the connection points. As a result, from the second condition, we're going to find that every single member in a truss is a two-force member. Big simplification. That's truly where our biggest simplification flows from. And last but not least, the loads are only applied at pins. So if you have a truss and you're going to load it with an external load, you don't apply that load in the middle of those slender members. You apply it only at the pins, and because of that, you are continuing to be able to treat those slender members as a 2-force member. So conditions 2 and 3 really keep us in the category of all members being 2-force members. So as a just a review, what is a 2-force member? It is a rigid body in which you have only forces that are collinear and no moments. So that simplifies our analysis. Okay, trusses come in 2 flavors depending on how many dimensions we want to support. We can have a plain truss, in which the members are put together to form a triangle. Up here at the top, this would have a sort of a pin connection, and you have a pin connection down here at this support, and then you have a roller pin connection here. This is what's called a simply supported truss, and even though it's only got 3 members, it is indeed a truss. It's a simple truss. Our 3D equivalent of that is a little pyramid, which is basically 4 triangles put together, and of course all of their connections would be, think of them as a ball and socket. And of course we're appropriately loading each of our trusses at a joint with an external force and supporting at the joints. In each of these cases, we can build from our simple truss, either our triangular plane truss or our pyramidal space truss, by just adding more of the same unit. So I would add more triangles or add more pyramids, and I could build up any number of different truss styles that are intended for specific applications to optimize different needs. Depending on what textbook you have, chances are you have examples of different classic style trusses, Pratt and Howe and different types. Many of these are used for things like architectural roofing, arches, bridge supports, and what have you. Transmission towers, electricity, communication cables are another typical use of trusses, both plane and space trusses that you'll see every day. Why do we have so many different types? Again, they each optimize something else. Efficiency in terms of load carrying capacity versus the truss weight. Really important if you've got to truck the thing out or float it out somewhere to assemble it in a remote location. You want it to carry a lot more weight than it itself has, because you might have to carry it with something else. You may have to design for clearance, like under a bridge, have a big barge or a big tall ship be able to go underneath it. You might have wind loading coming in crossways in addition to maybe your main static and dynamic loads, something that has happened on a lot of suspension bridges and with bad effects when people didn't plan for it. And you may be planning around just an overall shape envelope, especially for an architectural application, holding up some crazy type of roof. Okay, so we're going to zero in on how we're going to treat our 2-force members, since that's all we have to do with a truss. All we got is 2-force members. So let's look at cool ways that we can see how a 2-force member is loaded. We kind of got 2 ways. So here's one way. We have our 2-force member, and we can pull on it. We can put it in tension. So we got a pin connection over here, or a ball and socket connection, and we have a net force at that end of a value P, and it's pulling, and you have a net force at the other end, and it's pulling. And given that it's a straight bar, the line of action of the forces are of course collinear for a 2-force member, and they are also in the direction of the member. So that's another aid to equilibrium. So we would say that because the forces being applied at both ends are pulling away from the member, that the member would be in tension. Now, if we want to check that, or just take a peek inside of our 2-force member, here we're going to take our first foray into internal forces. We're going to cut that beautiful member in half, virtually of course, and we're going to create a cut section. Now, we cut this, but we didn't take the body out of equilibrium. These 2 cut sections aren't flying off in the direction of the applied force at the joints. They're just sitting there. The whole thing is still at equilibrium. So there must be some force on each cut section keeping it from accelerating, because the joint applied forces haven't gone away. We still have a force P at this joint end and a force P at this end. So what's actually happening is that the opposite structure on the other side of the cut is applying the force needed to keep each cut section in equilibrium. So these two P's in the middle here represent what's called internal forces that you can think of as reflecting across the mirror. So from this lower half of the cut, it's being yanked on by this upper one, and this upper one is being yanked on by the lower one. So again, we can see a little Newton's third law, action and reaction, going on there. And in fact, that's the law we invoke to model those internal forces when we make that virtual cut. But if you're ever lost, just think, I make a cut and I have to keep both cut sides in static equilibrium. So what forces, moments, etc. In the case of a two-force member, it'll only be one force and it'll be collinear with your original line of force. What will have to be applied to keep my cut section in static equilibrium? And that will help you understand exactly what force is being applied internally. Okay, well, there's one other way we can load a two-force member, and that's instead of yanking on it, we can push on it. So here we've got even a little dot representing a pin joint. So rather than the forces P pulling that slender truss member, now it's pushing. So this member is in compression. And of course, if we were to cut it and look at the internal forces throughout the member, we would see that each member now has to push on the other side of the cut to keep each cut section in equilibrium. So we will use this method of cutting through truss members very specifically in what's called, not surprisingly, the method of sections, which is a really good shortcut method for solving for forces in individual members without having to solve them in all the members. But you'll use this the same kind of idea of cutting and looking at what forces across the cut have to keep both halves in static equilibrium. That is a very fundamental tactic that you'll use from this point forward in your study of statics. But trusses are a great place to start because they're two-force members. So if we want to look at what happens with non-truss structures and when we don't have a two-force member, we can take a look at this little guy. Here's one cut section of what looks kind of like a slender member from something that's not a truss. This member was subject to bending moments or shear forces. It was not a two-force member. It had some other force acting on it. So if I cut it, I would have to apply a lot more than another force that's in line with the length of the member. We would only have force A if this member had come out of a truss. But if it came out of something that was not a truss, and therefore this hadn't been a two-force member, we'd have to have two other force or moments coming from the other part that we cut it away from. We would have to have another force at right angles to our normal force A, and normal meaning normal to the cut surface. A also means axial force. And we'd have to have what's known as force V, that's V by convention. It's called shear force, because if you're talking about a long straight truss member or beam, and of course V would be 0 if it was a truss. If you had a long straight member of some frame or a beam, it would put that beam into shear. And the concept of shear is something you'll study quite a bit more in mechanics of materials or material science if you go that direction. Furthermore, you will have to apply a bending moment on that cut section. So the other half of whatever we cut this bit of rigid body away from, it's going to have to apply not just one force in the direction of that body like we did with a truss. It's going to have to apply a shear force and a bending moment, very likely. So you've got three forces or moments being applied across a 2D cut section if we don't have a two-force member. So A, otherwise known as N for normal, V and M. So we'll get to that later with beams and look at V and M specifically. But with trusses, yay, We only have A if we're going to cut a truss. So just a word about pin loading. So one of the requirements for a truss is that not only are the members held together with pins, which render them two-force members, it keeps them from having an applied bending moment or shear stress. If we apply another force to the truss, which we're probably going to do because that's probably why we built the truss, those external forces are also going to have to be applied only at the pins. So we've got a little truss here supported by two hinges at Q and R. We're not going to apply that 10-pound load in the middle of one of these members. If we did, this wouldn't be a truss, okay? It wouldn't be a truss. So also remember things like distributed loads. If we had a water or wind blowing down on this such that we had a distributed load down this member, we also wouldn't have something that we could analyze like a truss. It would still be slender, but we'd have to analyze it with our more general conditions of equilibrium. We couldn't use all our shortcuts that we do for a truss because those only work for two-force members. But since in a truss everything has to be applied at the joints, we can use action-reaction at the pins and give ourselves an extra free body diagram specific to those pins, which sometimes really facilitates our analysis. And you may have already done this in your study of just general equilibrium analysis because it's allowed. You can do an FBD about anything. But with trusses, it's particularly useful because all the loads have to come at the joints. So if you want to FBD the pin at any truss, you can often pick up a very handy set of equations of equilibrium and apply Newton's third law. So in the case of the pin here at point B, we have 10 pounds of force coming downward from our external loads, and then we can assume, very likely, that we're going to have upward forces in the direction of member QP and PR coming up, and we could do a little equilibrium analysis if we knew these dimensions and we knew the angles of QP and R, and we could solve for QP and QR in terms of this applied load and that angle. And then here the trick is, if each of these members is pushing up on the pin, by action-reaction, by Newton's third law, the pin is pushing on the member. So if I were to do an FBD of member QP, had I solved, say, for force QP using my pin FBD, I'd have to make sure I put it in the opposite direction if I were to do an FBD of the member. So if the member's pushing on the pin is pushing on the member. If the member is pulling on the pin is pulling on the member. So just remember to apply Newton's third law when you're going between force members, our two force members that make up a truss, and the pins that connect them. And that will save you the misery of some sign errors. Simple Newton's third law. And that is it for our intro to trusses. The next lecture that you should get should be the method of joints, where we will use this very tactic and put each joint of a truss individually into static equilibrium and solve for the unknown forces in members and march our way from pin to pin to pin through the truss until we know all the forces. And that is known as the method of joints. So that should be your next topic, followed by the method of sections for more cutting. So enjoy.